show you that. I'm going to show you the, okay, so let's go here. Okay. All right. I'm going to rewind this thing. Okay, so I'm going to stop this. Okay, where are we going? Escape. Okay, so let me just show you what is, click cancel here. Okay, this is what we're going to do. All right, let's share that. Okay, so we are, okay, some important dates. All right, so just 4 weeks left, right? Just 4 weeks left. We have iReady testing next week, 13th through the 17th. So your math and English, make sure you do those so that we show some growth and you show some growth. I'm going to be at the Toledo Zoo on the 23rd, the Thursday in a couple weeks, 3 weeks. Okay. But I know that the Cincinnati Zoo and Columbus Zoo and I think Cleveland are all there in there. So get involved in that on Thursday, right? And then you can log that as an offline tracker time, right? We have one big last test that's on the 24th. Okay, so Friday the 24th is another last 60-point test. This last week, we'll be talking about the universe, but it's all bonus assignments, so you can catch up your score. So make sure that you're testing, you're doing your assignments in the order I asked you to do. Remember, so this week, what you want to do is week 15, get that done, right? Before you go on, get that done before you go on to anything old, right? So if you want to make sure done first, okay, get it done before, and you'll notice that the due dates are different for this week. All right, so I think I have a due date week 1 assignment. Week 15 assignment 1 is due on the Wednesday. Week 2 assignment 2, week 15 assignment 2 is due here, and then the test or quiz is due here. Okay, so instead of giving the weekend, right? So to check your grades, make sure you check them, right? If you've got, let's say, a 6 out of 15 on an assignment, okay, you remember you can change that to 15 out of 15, and you can get 80% in this class if you make sure you get to 15 out of 15 on all those assignments, because those are 2 assignments, and your quizzes don't have to be perfect to get that 80%. Okay, so you can make sure that you're fixing those. All right, can contact me if you have any other questions, but remember, week 15 first, then go back to week 14. So next week it's week 16, and then you can fix week 14. But today what we're going to be doing is week 14. Okay, I haven't graded the assignments 1 and 2 yet, right? And I also have the quiz that's due tonight. So I'll be grading the assignments today, giving a 0 for those auto-graded ones. So make sure you get those done. Okay, so what we're doing today, we're going to be talking more about waves. Okay, so energy waves. And so this is, you should know something about electromagnetic waves. We'll go over some things. We should know that the relationship between the wavelength, frequency, you should be able to know those words, right? And again, most of our tests are on vocabulary. So make sure you are using your notes or writing down your notes. Describe the relationship. You should know something about that already. So let's go through here. Okay, so remember, a wave is a traveling disturbance, right? So you sticking your finger in the water, dropping a rock into water causes the energy to travel through the medium, also known as propagation, the movement of the wave. What the basic idea, what we wanted to talk about, is that the energy moves through, but the material it moves through does not move. It just moves up and down or vibrates, but it doesn't go to the end of the wave. Okay, so matter does not move, but the energy does. All right, who else came in? Hey, DeAndre, good to see you. Carmen, good to see you. And so those are the bottom line is matter doesn't transfer through a wave. It just vibrates back and forth and goes back to its original place. And but the energy travels through. So two different kinds, mechanical waves and electromagnetic. So mechanical waves come in two varieties, longitudinal and transverse. Longitudinal are the long waves. They travel the same direction as the disturbance. Transverse waves are like water waves. They bob up and down, and the energy goes in different direction than the transfer of energy. So the energy vibrates the particles up and down, and then the waves go through to the right. Okay, electromagnetic waves do not need a medium. They used to think that in the 1900s, they used to call that the ether, but they found that there's nothing there. So light, microwaves, infrared, X-rays, ultraviolet, and radio are what we're looking at this week in more detail. Okay, so just as your review, the displacement from the rest period. So this is looking at a wave from the side, like a water wave from the side. There's a crest, the top of the wave, trough, the bottom of the wave. And we measure these waves, and we call that wavelength, or the letter lambda. Lambda is what we use for that. It looks like a stick figure without a head, or just the bottom part, I should say. Amplitude is how tall the wave is, and that usually measures the energy. So here is the longitudinal wave showing you a slinky where you're pushing on one end and the wave is going through the slinky to the end. The slinky itself doesn't move all the way to the end, just the vibrating coils hitting each other. Transverse wave, you've got a source that goes up and down, and the energy still goes to the right, but you've got waves going up and down here. Okay, so this is one thing that you want to make sure that you take a look at. Look at the electromagnetic spectrum. Here's a good example of the relative size. So we start with the radio waves. They're about the size of a football field or a soccer field, right? Radio waves can vary in size from the size of the house to larger, and they are measured in kilometers, or yeah, they're all measured in meters, but I usually talk about they're large by talking about thousands of meters. Baseball for the microwave, right? All right, it's about less than a meter, about half of a meter, maybe even because it's baseball size. We used to measure microwaves by actually putting a candy bar, like a Hershey's bar, in the microwave, and the waves would go like this through the candy bar, and there would be places on the candy bar, because candy bar is about 6 inches, and it would be melting at those 2 points. It would keep the rest of the microwave. Again, that's one of the reasons that we do this, we turn the microwave as a carousel, or turns so that evenly heats, but it only heats at those 2 points. So I have a microwave here that goes back and forth rather than turns. It's kind of interesting, back and forth. So that shows you the wavelength there. Okay, as we get down to infrared, it's about the size of a cell. Remember, infrared is you can see that they have infrared cameras, and infrared cameras can feel the heat. I think also Predator, if you watch the movie Predator, the alien was able to see your heat signature, right? So, and then we get into visible light, which is very small, right? We can see the visible light, but we can't see the waves themselves. And then as you get into X-rays, they're small enough to penetrate the skin of your body and see the bones. Then we get to gamma rays, where they're so small that they can pass through just about anything. Okay, so we'll be talking about those in more detail. So the energy, remember, energy is the ability to do work, kinetic, potential, thermal, chemical, nuclear, sound, and radiant. We'll be having a test on all these energies on the 24th. Mechanical energy requires a medium. Medium could be water, solid, or gas, air. We mostly see. Hi, Kylie. We always see sound waves. We don't see them, but we can hear sound waves in air. If we did an experiment where we took the air out, you would tell that there was no sound, right? Hey, I'm glad you made it. Better late than never, right? So electromagnetic, no medium needed. These waves travel through the emptiness of space. They are vibrating electrical and magnetic fields together. All right, so together here, and I'll show you this video here. So you can see the light energy is going up, and the magnetic energy is to the right or to the left. So the up and down. So anytime an electric field is produced, you get a magnetic field at the same time. And we'll show you how that is. If you take a look at the modules, or in the modules, there are some FET simulations, and you can see how to make electrical energy from magnets, and you can show how you can make magnets from electrical energy. So here is a video. There we go. It's loading here. Try to get this to work. So we've got the light waves in the red and the magnetic waves going in the blue field here. Okay, so it begins with electrically charged particles. Vibrating charged particle causes an electric field surrounding to vibrate as well. The vibrating electric field in turn creates a magnetic field. So that's why they call it electromagnetic. They don't just call it electro wave. They call it electro combination magnetic. So they put those two words together. Right, here's another one of those. Electromagnetic wave is a type of transverse wave, right? So it's still, the energy is going to 90 degrees from the direction of the energy, right? And the energy is the wave itself. It's not moving matter. Right, so wavelengths, the relationship between wavelength and frequency. So we have to remember that wavelength is that measurement from height, crest to crest, or trough to trough, or you can also measure from any point as long as it's the same point on each place. Frequency is the number of waves traveling per unit time, and then wavelength is speed is wavelength times its frequency. So how long the wavelength is times how many waves per second. Okay, so one of the things that we want to make sure that we take a look at on your diagram, we have ionizing and non-ionizing. Okay, and ionizing is on the UV is not included in that, but UV is dangerous, so that's why we wear sunscreen. X-rays and radioactive elements. All right, anybody have an experience where you've had an X-ray like of your teeth, recently and they put that heavy vest on you and then the operator walks away? Anybody had their teeth cleaned or x-rayed recently? Okay. So, and you notice that the person walks away, right? The one that the x-ray technician walks away, goes into another room. Anybody else know that? Notice that? Anybody notice that the x-ray technician moves away? Yeah. So the reason they do, we can take so much exposure to x-ray. So like we have maybe one or two x-rays a year. An x-ray technician is exposing themselves to hundreds a day. So if you were not didn't have a lead shield or walk away, they would have some trouble. So they try to tell you it's not harmful to you, but the impression people get is, well, they're walking away, it must be harmful, right? So again, it depends on how many x-rays you get. All right, so EM spectrum, the entire range of EM is in order from increasing frequency to decreasing frequency. So the reason that this is, okay, we got radio waves, which are long, and the speed of a radio wave is 300,000 kilometers per second. Same way with a gamma ray, okay? But the wavelengths are smaller. So as we get to the gamma ray, and the gamma ray is, if the speed's the same but the wavelengths are shorter, that means you can get more of them through, more pass in a second, where radio waves less pass in a second. So that's big thing here. So let's kind of talk about, let's go through this video here and tell me if you can hear this. He did a really good job talking about the different kinds of rays.
Radiation,
here, okay?
causing horrible things like cancer and warmth and food and cell phones and sunsets since the beginning of time. What are we talking about? Welcome to another edition of I Don't Think That Means What You Think It Means. Radiation. It's when energetic particles or waves move through space, and it's pretty much the best thing ever. Radiation includes visible light, which is always bouncing off of stuff and then hitting our retinas, allowing us to not stub our toes and generally enjoy the splendor of the world. It's also what plants convert into the food we eat. Infrared, or IR radiation, which is this stuff that actually warms the Earth, so it's the reason that we're not all freezing to death right now. Microwaves, which not only heat up our hot pockets, but also transmit our cell phone calls. A huge amount of study into whether these microwaves cause cancer indicates that they probably do not, and the World Health Organization classifies them in the needs more study category, along with coffee and pickled vegetables. Radio waves, which carry, yes, radio signals, also 3G and Wi-Fi and all that good stuff. And then we have the extremely low and very low frequency waves, which aren't super useful but don't hurt anybody either. Unlike all of the above examples, some kinds of radiation can transfer their energy into atoms and ionize them, removing electrons, which is where the problems begin. When most people think of radiation, what they're really thinking of is this radiation, which is ionizing radiation, including X-rays that can ionize atoms, but it's generally worth it to take a peek at your broken bones. Ultraviolet radiation, which is mostly non-ionizing, but can excite atoms enough to cause some unwanted reactions, like in our skin, which is why we put on UV protection in our sunblock. Gamma rays, which are pretty much the worst kinds of all the radiations because they can travel through pretty much any material and then ionize an atom right out of your DNA, leading to some pretty serious problems. Now, thus far, we've only been talking about waves, but as I said at the beginning, radiation is energetic waves or particles, so there are some forms of radiation that are actually particles with mass. These kinds of radiation are only caused by nuclear reactions. An alpha particle is a flying bit of atomic nucleus, 2 protons and 2 neutrons stuck together. They're so big and slow that they don't generally cause much damage unless you ingest something that's emitting them. so I suggest you don't do that. Beta particles are energetic electrons that are more ionizing than alpha particles, less ionizing than gamma rays, so they cause some serious damage as well. So now you know. And if your friends don't know, send this to them, because if we use the word radiation like it's evil, all of the helpful forms of radiation might get angry and go on strike, and then we would all die. Thank you for watching this episode of SciShow. I don't think that means what you think it means. If you would like,
we would all die. I like that. Not being able to die. I like that a lot.
Radiation causing.
Okay, so if you take a look at this, so this is kind of a good picture of what it looks like to see a wave. Okay, so let's say these are the same length, and they are probably. So radio waves are the longest wave. We got one wave. And then microwave, we get a few more waves in the same amount of distance, and infrared more so. And then again, as we get to visible light, we have more waves until we get to gamma rays, where we can, you can't even count them. There's so many in this distance. So as we go from radio to gamma, the wavelength, the distance between waves gets smaller, and the energy gets larger. So that's the weird thing. So the energy of gamma is very, very high because so many small waves are going quickly, the same speed. They're just so many waves are passing at a certain time. And again, radio waves are very long and they take a lot longer to go. But the speed of a wave is still 300 kilometers per second. Just the number of waves passing through in a second is more. So that is, let me go here. So that is what they call inverse relationship. So as the wave size gets smaller, the energy goes up. So small goes up. So that's an inverse relationship. Long goes down. All right. So long waves, low energy, low frequency. Short waves, high energy, high frequency. Right. So high frequency equals high energy. All right. So electromagnetic waves travel very fast, 300,000 kilometers per second, or 300 million meters per second. Requires 8 minutes for the sun's ray to hit us. All right, and the moon to the Earth is only 1.3 seconds because of that distance. So the Earth and Sun are quite distant. Okay, so our sun is a source of energy that, with a full spectrum, and electromagnetic radiation bombards the atmosphere constantly. Right. And so gamma rays and X-rays and ultraviolet rays. So ultraviolet is not ionizing, but means that the high energy can knock off electrons. And we've talked about that. Gamma rays and X-rays. So ultraviolet rays don't ionize, but they do knock off certain things. That's why we wear sunscreen, right? You can get cancer over long exposures of sunlight, but you do need to get your vitamin D. So you need to get some, you get that even with sunscreen. So vitamin D is good for you. All right, so EM waves do not require a medium. Higher frequency, the more energy. Inverse relationship, wavelengths get smaller, the frequency gets higher. And all electromagnetic waves travel at 300,000 kilometers per minute, per second, right? Right? Crests and waves, crests and troughs, wavelengths, longitudinal and transverse waves. Okay, so let's take a look and see if you can read this and determine what this looks like. Okay, so we're going to do some little quiz here. All right, so let me get turn this off. Go back here, and I'll come to that assignment here. Okay, so reading this, if you can read this. Okay, it is gamma rays are less than 0.1 nanometers. Okay, X-rays are 0.03 to 3 nanometers. A nanometer is a billionth of a meter. And ultraviolet is 100 to 400 nanometers. So which would you say this was? Right? Gamma rays, X-rays, or ultraviolet? Gamma rays, X-rays, or ultraviolet? Okay. So what do you say? All right. So 200 nanometers. So, all right. Yeah. Thank you, Adriana, Chloe, Gabby, Rachel. Anybody else want to get in there? Grace, DeAndre, Brad, Blake, Aaliyah. Anybody want to get in there? Okay. So gamma rays are less than 0.1 nanometers. And the only one that actually showed 200 nanometers is the ultraviolet, right? The ultraviolet went from 100 to 400. So this is what this one was. So this one was your ultraviolet. Okay, let's take a look at the next one here. Same three. Okay, it is wavelength of 2 nanometers. Okay, so gamma rays says less than 0.1, so that's not it. And we said ultraviolet rays were 100 to 400. So the only one it could be was 0.3 to 3 nanometers. So that's the only one it could be is your X-rays. Thanks for getting there, ladies and gentlemen. So your X-rays here. All right, now this one is the smallest wavelength that we have on here. So we've already talked about X-rays. We've already talked about ultraviolet. So this is less than 0.01. So this is less than that. So it's got to be gamma rays, right? Got to be gamma rays. And this is something that's on your assignments this week, also on the test. Again, use your notes. It's always important to use your notes. I don't expect you to do this without notes. So this is something you could write down, but it also is in the notes in week 15. All right, so everybody got that one. All right, so the lower energy wavelengths, the longer wavelength, right? So let's take a look at this. What is 100,000 nanometers? Now look at these things. This one says nanometers. This one says millimeters. And this one says kilometers. So we're looking for nanometers. So it has to be which one? Yeah, you guys got it. It's got to be the infrared, 700 to 1 million nanometers, right, is your infrared, right? Okay, so this one asks you millimeters. So this one's not millimeters. This one's not millimeters. So what do we got? Millimeters. All right, and remember I said you had put a candy bar in a microwave. It's 6 inches long, and you'll see the places where it melts. So this is your infrared. Oh, sorry, microwaves. There we go. Okay, so this last one, you're going to have to use your notes. You're going to have to use 3 different things that are 3 different pages. And so visible light. So red is over here at 700, right? So that one's 700. And violet's over here at 400. So what is 530? Yeah, 5.3 nanometers, billionths of a meter. We can see those is your green light. Okay, so just kind of breaking this down, mechanical waves requires a medium, does not require a medium for electromagnetic, longitudinal or a transverse wave, only transverse wave for electromagnetic. And here's the different types. And this is the important part, can transmit energy but not matter. So it's not moving any matter. It's just vibrating. Okay, so today what you're going to do, all right, is exit quiz, and any of those assignments that you are for week 14. I have not graded week 14, assignment 1 and 2 yet. So you want to make sure you do that. Here is the exit quiz. It's a assignment again on how to read those charts and then decide whether it's gamma or infrared or visible light. Okay, so let us give you this. I'm going to go to the chat here, clear out the chat. Here is the exit quiz 5.6a exit quiz. Be careful on the spelling of your the spelling of this assignment, because you have to type in the words for this exit quiz. All right, and again, like I said, I will get you the big blue button link here in a second, but what I'd like you guys to do is make sure you check your grades, and if you have your grades, all your grades for the assignments are at 15, that's great. If you don't have all your assignments at a 15, get them up there, because all your assignments at a 15, and then if you've done your quizzes at a 60%, you should be able to get a B in this class, right? And so I'm going to put this link in here. I'm going to talk a little bit about what you should be doing here. Okay, so get W14 assignment 1 and 2 done today, because I'll be grading it at the end of this hour. Okay. All right. Get W14 quiz done today, because it says a quiz done today, because it is due today. I have also changed the schedule for this week's assignment. So I think that Wednesday, W15 assignment 1 is due, and Thursday, W15 assignment 2 is due, and Friday, W15 assignment, the quiz is due. Okay, so if you need any help from me, let me know.